in physics and BSc in mathematics from University of Michigan, Ann Arbor in 2017. So please go ahead.
Thank you, Farhat. Yeah, and just a little bit more word of background. So this work began on the old CMEC grant, and currently I'm sort of wrapping this up, and a paper on this is due to come out shortly. So I'm excited. Yeah, to sort of many of you have been involved in this work for a number of years, so I'm excited to share how it's evolved since CMEC has sort of moved on in the last year or so. So my talk today is on the effect of small magnetic fields on stimulated Raman scattering in the kinetic, inflationary, and strongly driven regime. And just to begin with a bit of background, so this work was sort of kicked off by a paper published by Ben Winjum, who's also a member of CMEC and who graduated from our group at UCLA back in around 2010, I believe. So in this paper in 2018, he showed that one can mitigate SRS in the kinetic regime by using small external magnetic fields. And this result is important because LPIs such as SRS have deleterious effects on ICF schemes such as NIF. And so, furthering our understanding of LPIs such as SRS, and in particular coming up with ways of mitigating LPIs is something of great interest today. So in particular, the CMEC group became interested in exploring these results experimentally. And that was sort of right around the time when I began my PhD. And so my job was to provide simulation support for their efforts. And sort of where that led us is to consider the effects of small magnetic fields on SRS in the parameter space more broadly. So specifically what I mean is that Ben in this paper considered drive strengths or laser intensities of moderate intensity, sort of corresponding to an average, the average speckle intensity on a NIF beam. However, beams of sort of order of magnitude higher intensity also exist and are important to study because they're more vulnerable to instability. And that's sort of the focus of my talk today. So the key point is that at stronger drives, the effect of the magnetic field is more complex than what was shown in this paper in 2018. We can see similar levels of reflectivity and even enhancement with the magnetic field due to competing effects. So just for those of you who aren't familiar, a quick word on stimulated Raman scattering. So this is a laser plasma instability where an incoming pump propagating through a plasma goes unstable and scatters into a backscattered light wave with frequency omega-1, wave number k1, and a forward-going scattered plasma wave with frequency omega and wave number k. And a really simple way to understand this instability is through the matching conditions. This is a really simple set of equations, but I think is quite powerful. It could take you a long way in terms of understanding the instability. So all that says is that the frequency of the incoming laser is equal to the sum of the two scattered waves, and similarly for the wave numbers. Yeah, sort of the thing to keep in mind here is that small magnetic fields affect the dynamics of SRS by altering the evolution of the scattered plasma wave. So by altering the evolution of the plasma wave, they affect the coupling and change the dynamics of the instability as a whole. So the outline of my talk, just to orient everybody, is as follows. We'll begin with 1D OSIRIS particle and cell simulations, and we'll sort of progressively add layers to the story from there. So within the 1D category, we'll first look at driven plasma wave simulations, where the B field will alter the evolution of plasma waves. Then we'll use what we learned there to understand how the magnetic field effects, fully self-consistent SRS, and in particular to compare moderate versus high intensity. And then we'll move from 1D simulations to 2D simulations. In 2D simulations, geometrical effects become important, and that sort of adds a layer of complication to the story, and adds important details. So to begin, what do we mean by small magnetic fields? So in the lab, these are order 10 Tesla, so perhaps not so small from an experimentalist point of view. But in terms of normalized units, these are very small fields. So they're fields such that the cyclotron frequency is much smaller than the plasma frequency. And this means that one cannot use the magnetized plasma dispersion relation used to derive, for instance, Bernstein modes. This assumes a phase mixing, which cancels out Landau damping, which this assumption doesn't hold for the fields which we consider. One can derive small corrections to linear theory. Here we're showing a result where the Landau damping rate is modified. However, the modification is, again, very small since this ratio is very small. And so the key point is that when we're talking about small magnetic fields, what we mean is that these plasmas can be treated as essentially unmagnetized as far as linear theory is concerned. So while the linear effects are negligible, what we'll see is that the effect of these small B fields on nonlinear plasma waves can be very significant. So here I'm showing a couple of images from some early work on this subject to demonstrate how this works. So on the left, we have a plasma wave traveling in the X direction and a magnetic field oriented in the Z direction. Now, these waves are nonlinear. This means they trap particles. So an electron gets trapped in this wave. Due to the Lorentz force with the B field in the Z direction, this particle gets accelerated across the phase front of the wave. And of course, the magnetic field does no work. So it's the electric field from this plasma wave, which is doing work on this particle. And in this way, the result is that this particle, as it's accelerated across the phase front of the wave, extracts energy from that wave and damps it. Another way of visualizing this is by looking at a particle orbit in phase space. So Vx is on the x-axis and Vy on the y-axis. And in this example, we have a plasma wave traveling in the y direction. So a particle traveling near V phase gets trapped. It's oscillating it's oscillating in the wave, bouncing back and forth. As it's doing that, it's being accelerated by the magnetic field. So it's gaining energy in the x direction. And then eventually that particle gains so much energy and/or the wave is damped sufficiently such that the particle can be detrapped. And you can see that then it leaves the wave and executes cyclotron motion in the background plasma. And you can see that this particle has gained a significant amount of energy, or its velocity has increased significantly compared to where it started. And that energy, of course, came at the expense of the wave. So what we see is that small magnetic fields provide a mechanism through which these nonlinear plasma waves can be damped through resonant wave-particle interactions. Another sort of useful thing to keep in mind is, so we just saw how a particle orbit might look in phase space. It's also interesting to understand, or useful to understand, how the distribution function evolves in phase space with and without a magnetic field. So on the left, as a nonlinear wave is driven up without a magnetic field, it traps particles and you wind up with this flattening of the distribution function. With the magnetic field, on the other hand, what we see is that particles become detrapped and the distribution function remains more Maxwellian. And this will have important implications on how these waves evolve, which I'll touch on briefly. So a really useful way to illustrate this, and in fact to study it as well, is through driven plasma wave simulations. So these are very simple setups which allow us to isolate and understand the physics. So these are 1D, periodic, and single wavelength simulations. um, sorry, 1D periodic single wavelength simulations will ponderamotively drive up a plasma wave for a few plasma wave periods, and then we'll shut off the driver and watch how the waves evolve over the duration of the simulation. A couple of important parameters: K lambda Debye is about 0.3, so these waves are in the kinetic regime. And the cyclotron frequency, again, much smaller than the plasma frequency, about 10 to the minus 3, corresponding to about a magnetic field strength of 10 Tesla. So here's the result. What I'm plotting is the mode amplitude, which we've driven up as a function of time. Early on, we drive up the wave, the drivers shut off, and we watch how these waves evolve. Now, initially, everybody, no matter the magnetic field strength, so here what I'm showing is the three different curves are B equal to 0, B equal to 30 Tesla, and B equal to 60 Tesla. They all see this initial period of linear Landau damping, but then it's after this where their evolution is significantly different. So first for B equal to 0, as the waves slosh back and forth in the wave and give energy back to the wave, we see oscillations at the bounce frequency. Then as these particles, the trapped particles, continue to bounce back and forth in the wave, they phase mix. We get that flattening of the distribution function as we saw. This comes with a nonlinear frequency shift, so a negative frequency shift in the plasma wave, a negative delta omega. And finally, we get this evolution to an undamped mode. Now, with the magnetic field, on the other hand, we see oscillations at a modified bounce frequency. This was predicted in that early work by Dawson, which I had a citation to earlier. So oscillations at a modified bounce frequency. But then, as we described before, the magnetic field damps these nonlinear waves by accelerating particles across the phase front, and it prevents this evolution to an undamped mode. Now, this is all important because the nonlinear evolution of these plasma waves plays a critical role in the dynamics of SRS. And this is particularly true in the regime which we're interested in, which is called the kinetic inflationary regime. So kinetic, I touched on this before. This is characterized by K lambda Debye of about 0.3. This means that the phase velocity sits in the bulk of the distribution function, and so resonant wave-particle interactions are important and alter the evolution of the waves. In particular, they alter it in such a way that gives rise to this process called kinetic inflation. So kinetic inflation is a way in which SRS evolves where the instability starts off in this strongly damped regime characterized by gamma 0 over gamma p being less than 1. So gamma 0 is the growth rate of the instability, gamma p is the plasma wave damping rate. So we start off in this strongly damped regime where linear theory would predict very little growth of SRS, but then because we get this evolution to an undamped mode, gamma p goes to 0, so this ratio can become much larger than 1. The instability, therefore, can transition from strongly damped to weakly damped convective, or even absolutely unstable. And as a result, we get much higher levels of growth compared to what linear theory would predict. And so you can imagine that when inflation is important for growth, this external magnetic field would mitigate SRS because it, prevents this evolution to an undamped mode. It prevents the evolution out of the strongly damped regime. So this is true when gamma 0 over gamma p is small. But remember, I mentioned in the beginning, the regime sort of that we're interested in is this more strongly driven regime. And as we increase the intensity, gamma 0 gets greater. And so this ratio will remain less than 1, but it will get a little bit greater. And so this will reduce the importance of the fact that the magnetic field damps plasma waves, as we'll see. So indeed, what we see is that the effect of the magnetic field is different at moderate intensity versus at high intensity, partially, as I'll explore, as a result of the fact that gamma 0 over gamma p changes. So here what I'm plotting is reflectivity as a function of drive strength, laser intensity. Equivalently, I could have put gamma 0 over gamma p on the x-axis here. That might have been a useful thing to do. So what we see is that reflectivity near threshold, reflectivity is reduced quite significantly, or SRS, reflectivity from SRS is reduced quite significantly by around a factor of 3 here. But then as intensity increases, we see similar levels of reflectivity with the B field, or even a slight enhancement due to the magnetic field. And what I'll try to show over the next coming slides is that this isn't simply because inflation is less important at high intensity. In fact, it's because there are competing effects of the magnetic field. So on the one hand, it mitigates kinetic inflation and therefore suppresses SRS to the extent that inflation is important for growth. But also another result of the fact that plasma waves are damped by the B field is that the recurrence pattern of the instability changes. And especially as inflation becomes less important, this can result in an enhancement of SRS. So in the next coming slides, I'll attempt to illustrate this by investigating a couple cases from this curve. So starting out at this case near threshold, we see that an external magnetic field mitigates SRS by around, reflectivity is reduced by around a factor of 3. And notice that this ratio, gamma 0 to gamma p, the growth rate to the damping rate, is about 0.37, so much less than 1. But it's not just the case that, reflectivity is very different between these two cases. The recurrence pattern or the spatiotemporal nature of growth, saturation, and recurrence of the instability is qualitatively very different between these two cases. So for b equal to 0, first of all, just to orient, so what I'm plotting here is plasma wave activity, so the longitudinal electric field in space versus time. And remember, these are 1D simulations. So what's happening here is the pump enters from the left, propagates to the right. Initially, we get a couple of smaller bursts, and then here we see the first major burst of SRS growing up. So what's happening is the pump is going to the right, it drives up some SRS, it goes unstable, and the backscattered light travels from right to left across the box. As it does, it drives up this packet of plasma waves, so it's traveling from right to left, extracting more and more energy from the pump, and producing this large plasma wave packet. And finally, this burst saturates as that backscattered light leaves out of the incident boundary. And then what happens is this packet, which was driven up, remember, it has evolved to an undamped mode, and so it propagates across the box here. As it does, the pump is now able to come back into the plasma. It scatters off of this packet, but since this packet has undergone a nonlinear frequency shift, which is part of its nonlinear evolution to an undamped mode, the backscattered light, in order to maintain resonance with the pump, is upshifted. And so therefore, as that backscattered light travels through the background plasma, it drives this beat pattern in the background plasma. Since it's, you can sort of think of it similar to driving a simple harmonic oscillator off of resonance. And then finally, what happens is once this packet has convected 1 to 2 gain lengths into the box, so the gain length here is about 500. So once this packet has convected far enough, there's enough room in the wake of the packet for the pump to drive up a new burst of inflationary SRS, and then the process sort of repeats from there. So the recurrence pattern is we have these large bursts of SRS interspersed with smaller bursts. The smaller bursts have recurrence, which is determined by the magnitude of the frequency shifts. So 2 pi over delta omega predicts the spacing between these bursts. And the spacing between these larger bursts is essentially the time that it takes one of these packets traveling at the group velocity to travel 1 to 2 gain lengths, plus, of course, the time that it takes the backscattered light to get back to the incident boundary. With b equal to 60, the recurrence is very different. So again, we get an initial burst driven up. So the pump's entering from right to left. A backscattered light travels from right to left, driving up a packet. But then this packet is so strongly damped that the pump essentially, other than a little wisp here near the front, the pump doesn't interact with this packet very much at all. Instead, it passes right through and travels into background plasma, which is unperturbed since this packet has damped away, and drives up another burst with very similar profile to the original one. And so we get this uniform train of pulses. And in this case, recurrence is determined by simply the amount of time that it takes the pump to travel 1 to 2 gain lengths, plus the amount of time that it takes the backscattered light to travel that distance back. So basically 1 to 2 times the gain length multiplied by 2 to travel back and forth. So essentially 1 to 2,000 should be the spacing between these bursts, and indeed that's what we see. So to summarize, we sort of, we have a significant reduction in reflectivity, but the recurrence pattern is significantly different here. We have these large bursts interspersed with smaller ones, and here we have this uniform train of pulses. And I mentioned that there will be competing effects, but so far there's no evidence to that. But this will change as we go to higher intensity. So at high intensity, now we're considering this case in the saturated part of the curve at VOS of 0.028. Here we see similar levels of reflectivity and even a slight enhancement with the magnetic field. Here we're still in the sort of strongly damped regime or the inflationary regime. Gamma 0 is still less than omega p, but it's larger than it was before. So maybe this goes partway to explaining why reflectivity is similar. And I'll come back to that in a second. But even though reflectivity is similar across these cases, we have still very different qualitative spatiotemporal dynamics of the instability. And I'm also showing a 120 Tesla case here, which I'll also get to in a second. So for b equal to 0, we again see many of the same features which we saw before. I apologize, this image is perhaps a little bit small, but we have packets convecting, the pump scattering off of those frequency shifted packets, driving beat patterns in the background plasma. Things are significantly more complex here just because the gain length is so small. And so you can have many packets existing simultaneously. They can interact with each other, leading to incredibly complex dynamics. But overall, sort of the main features are very similar to what we saw before. With b equal to 60, things are significantly cleaner, but also probably a little bit more complex and noisy than they were in the previous case. This is because, the pump is, or the drive strength is stronger relative to the damping rate of these packets. So the pump is able to scatter off of some of these packets, the previously driven up packets before they damp away. But overall, the recurrence pattern is significantly cleaner and very different compared to b equal to 0. We can regain much cleaner recurrence by doubling the magnetic field, so going to 120 Tesla. Here again, basically what's happening is the plasma wave damping rate is increasing relative to the drive strength. So we, reduce how much the pump is able to interact with previously driven up packets, giving rise to a much cleaner recurrence here. So returning to reflectivity, to 0th order, reflectivity is quite similar across these 3 cases. But you do notice that with increasing magnetic field, you get a slight increase in reflectivity. And this trend, it turns out, holds up over an ensemble average of simulations. So over an ensemble average, we have increased reflectivity with increased magnetic field strength. So each of these data points is average reflectivity across 3 different simulations. And what this suggests is that the reason that we have similar reflectivity here is not simply because inflation is becoming less important as the drive strength is increasing, but rather that there are competing effects of the magnetic field. And in fact, that this alternate recurrence pattern actually leads to an enhancement in reflectivity. So to summarize the 1D results, we've seen that the effect of a small B field on SRS is different at moderate intensity versus at high intensity. And this is due to the fact that by damping plasma waves, the B field has competing effects on SRS. So on the one hand, it mitigates kinetic inflation. This results in a suppression of SRS. But on the other hand, the damping of plasma waves also results in a significantly different recurrence pattern. And this can enhance SRS, in particular as intensity increases and inflation becomes a little bit more important. Or sort of another way of phrasing this is that at lower intensity, these competing effects are not on equal footing. And so inflation is very important, and we very clearly see suppression of SRS. But as intensity increases, these effects are on a more equal footing, and therefore we can see similar levels of reflectivity or even slight enhancement with the magnetic field. Okay, so returning to the outline now, just to reorient ourselves, we've covered the 1D picture, but where we're heading next is to look at 2D OSIRIS particle and cell simulations. And here we'll see that geometrical effects play an important role. And so we'll sort of do the same thing. We'll start with looking at 2D evolution of driven plasma waves with and without the B field, and then we'll touch on fully self-consistent simulations of SRS. Just see how I'm doing on time. Okay. So 2D driven plasma wave simulations, the setup is very similar to what it was in 1D, but with a few important differences. So we'll do both single wavelength and multi-wavelength simulations. In 1D, we didn't show any multi-wavelength results just because the conclusions that we drew remain unchanged when going from single to multi. But here we'll show that there are some important differences. Again, we'll drive up a wave over a few periods and then watch it evolve. K lambda to bi is still 0.3, so we're in the kinetic regime. In the transverse direction, now in 2D, we'll use a Gaussian profile to sort of simulate an F8 speckle. So the simulation setup is shown here on the right. In the transverse direction, x2, we have a Gaussian profile. The waves have a K in the x1 direction, and they propagate from left to right. We'll again consider small magnetic fields, but this time we'll have two different polarizations of the magnetic field. So just a word on that. So if the magnetic field is oriented in the 2 direction, so across the simulation plane, that means that particles will be accelerated out of the plane of the simulation and therefore will remain in the speckle. And so the trapped particle motion in that case is quite similar to how it is in 1D. By contrast, if we polarize the magnetic field in the 3 directions, so out of the plane, the result of that is that particles will be accelerated across the speckle, which has, finite width. So when the magnetic field is oriented in the 3 direction, trapped particle motion is more true to 3-dimensional physics. And of course, at the end of the day, you care about 3D physics is what you care about. But both of these are useful because it's sort of, by comparing them, it allows us to isolate the effects of a finite speckle. And then finally, we'll consider 2 plasma wave amplitudes. So the higher amplitude corresponds to the max plasma wave amplitude, which we see in our SRS simulations. And the smaller of the 2 is a factor of 10 lower than that in terms of amplitude. And again, in 1D, we only showed the low amplitude case because the results were unchanged across these 2, but in this case, we'll see that there are some important differences. Okay, so here I'm showing or comparing the 1D versus the 2D results at the low amplitude. So on the left is the 1D result, which we saw previously. On the right is the 2D result. I've got a 0 Tesla magnetic field and then a 30 and 60 Tesla magnetic field oriented in both the 3 and the 2 direction. So the first thing we notice is that in both cases, plasma waves are damped by the magnetic field. Interestingly, though, we notice that the damping is slightly stronger when the magnetic field is oriented in the 2 direction. So for instance, comparing the orange to the red curve, or the green to the purple, we see that when the trap particle motion is more 1D-like, with the field oriented in the 2 direction, the damping is stronger. Comparing the B equal to 0 cases, previously we had this evolution to an undamped mode, but now after a couple of bounce frequencies, we see that, or bounce periods, we see that the wave ultimately damps away. And so I suppose what we're seeing so far is that it would appear as though geometrical effects are leading to less pronounced differences with and without the magnetic field. And we can explore that a little bit more on this slide here. So what I'm showing on the left is the transverse evolution of the wave as a function of time. This is for B equal to 0, for B equal to 60, oriented in the 2 direction, so 1D like trap particle motion, and 60 Tesla oriented in the 3 direction, so 3D like trap particle motion. For B equal to 0, we actually see that on axis, we do, after a couple bounce periods, have this evolution to a relatively undamped mode. However, when the transverse extent of the wave is considered, we see that the reason the wave damps away is due to transverse localization. So this is where particles initialized outside of the wave stream into the wave and damp it from the outside in, giving rise to this triangular shape, which we see here, and ultimately the damping of the wave. With the magnetic field, we see evidence of transverse localization, which is characterized by this triangular shape, but it would appear as though the damping due to the B field dominates here, and so we have much stronger damping with the magnetic field than without. So sort of to summarize, we see that at low amplitude in 2D, on axis, things actually look quite similar to how they did in 1D. But when the transverse extent of the wave is considered, the total energy is considered, we see that differences are less pronounced due to geometrical effects. Okay, so that was the low amplitude case. Now let's consider the high amplitude case, and we'll see that some new effects emerge here, which alter the conclusions. So first of all, we see that the evolution for B equal to 0 is actually almost exactly the same as it is with the magnetic field when it's oriented in x2. So that's the red, blue, and purple curves here. And when the magnetic field is oriented in the 3 direction, so more 3D-like trap particle motion, we see that the waves actually damp more slowly with the magnetic field. So it's the opposite of what we saw in 1D. And the reason for this is wavefront bowing, which is what I'm illustrating on the right here. So here I'm showing snapshots of the fields at different key moments in time on different rows. And on the left-hand column is the case for B equal to 0. On the right-hand column is the 60 Tesla case with the magnetic field oriented in the 3 direction. So focusing first on the B equal to 0 case, you can see that we're driving up a wave here. But remember, it has this Gaussian profile. That means that the amplitude on axis is higher than it is off axis. And the result of this is that the nonlinear frequency shift is higher on axis. It's more nonlinear than it is off axis. So the frequency shifts down. As a result, the phase velocity, omega over k, decreases. And so the sort of central core of the wave begins to lag behind the wings a little bit. Ultimately, this gets so extreme that the structure of the wave can no longer be maintained, and ultimately the wave breaks up as a result of this. Now, the magnetic field, if you think back to that image of the evolution of the distribution function. The distribution function stays more Maxwellian with the magnetic field since particles are detrapped. Therefore, the frequency shift is smaller and wavefront bowing happens to a smaller degree. And so the wave is able to sustain itself for a longer period of time, leading to the result that we see on the left here. So yeah, wavefront bowing leads to, at this high amplitude, wavefront bowing is a new effect leading to the breakup of waves, and the B field reduces wavefront bowing because it reduces the nonlinear frequency shift. So we see the emergence of a competing effect of the magnetic field on plasma wave evolution in 2 dimensions. And just one more point of interest on this slide. Take a look at this image on the bottom right here. What you see is an asymmetrical damping across the speckle with the magnetic field. So the damping is stronger on the top than it is on the bottom. And remember, particles are streaming in that direction. They're streaming from bottom to top. This suggests that it takes some time for the particles to get to a point where they efficiently extract energy from the wave. And this is further evidence on top of the differences we've already seen between X2 and X3, further evidence that the finite width of the speckle leads to less effective damping with the magnetic field. Okay, so the last sort of layer which I'd like to add is to consider multi-wavelength simulations. And here we'll see that yet a new effect arises which further alters plasma wave evolution. And in particular, the effect that I'm talking about is this trap particle modulational instability, or TPMI. So TPMI is where we're driving up a mode at a particular K, but then that mode goes unstable and produces modes at sort of a spread of Ks near the driven K. So we get modulations in the mode which we're driving up. So this is what I'm showing here. So we're initially driving up this wave. We'll get modulations in both the longitudinal and transverse direction of the wave, resulting in these sort of holes scattered throughout the mode which we've driven up. And what you notice here is that TPMI seems to affect both cases to a similar degree. We still do see some of those characteristics that we saw from the previous slides. We get this central filament forming for B equal to 0. We see this asymmetric damping with the magnetic field. But overall, TPMI seems to act similarly. It plays an energetically significant role here, and the result is that it further decreases any differences that we see in plasma wave evolution with and without the B field. So in this case, the 3 curves, 0, 30, and 60 Tesla, are all but indistinguishable here. If you were to give me this plot without any labels, I wouldn't be able to tell you which one was which, except for maybe due to the difference in the bounce frequency. But you get my point. Okay, so just to summarize the 2D driven plasma wave simulations before we move on to the final part of the talk, which is the 2D simulations of SRS. We saw before that in 1D, plasma waves are always damped by the magnetic field. But in 2D now, we've seen that the plasma wave evolution is more complex due to the emergence of geometrical effects. And overall, the result of that is to make it so that differences with and without the external magnetic field are less pronounced in 2D than they were in 1D. So just to summarize those effects, so the finite width of the spot size limits how effectively the magnetic field can damp plasma waves. Second, wavefront bowing emerges as an effect. It leads to filamentation and plasma wave breakup, and the magnetic field prevents this from happening. And finally, TPMI plays a significant role in the evolution of plasma waves, and it doesn't seem to be affected by the magnetic field at all. Okay, so now building on that foundation, what we'll do is consider how yeah, how those results affect the evolution of SRS in two-dimensional simulations. And what we'll see is that generally the 1D trends hold up in 2D, but there are subtle differences due to geometrical effects. So on the left is the old 1D result, reflectivity versus intensity with and without the magnetic field. And on the right is the same thing in 2D with a 60 Tesla field in the 3 and the 2 direction. So in 2D, the onset threshold is higher just because we no longer have effectively a plane wave. We have a focused Gaussian beam. So the onset threshold is higher. Near threshold, the magnetic field still reduces reflectivity from SRS, but perhaps to a smaller degree than what it did in 1D. So, maybe by a factor of 2 rather than by a factor of 3. We still get a crossing of these two curves, except now this crossing occurs closer to threshold than it did in 1D. These are all a result, or all these things I've mentioned so far are a result of the fact that plasma wave damping is less effective in 3D, or in 2D rather, than it is in 1D. Sort of in 1D, you can think about it as by going from 0 to 60 Tesla, you're displacing this curve to the right. In 2D, you're doing the same thing, but the curve is displaced not quite as far to the right. And furthermore, you can see that when the trapped particle motion is more 1D-like, so with the B field in X2, the curve is displaced a bit further to the right. Yeah, and then finally, when we get to this saturated part of the curve, what we see is that we still get an enhancement, except perhaps a slightly larger enhancement than what we saw in 1D. And this bears a little bit more looking into. So for the next couple slides, I'd like to focus in on this result and explore some new things that are happening there that aren't happening in 1D. So what I'm plotting here is, for this case, we're plotting the longitudinal electric field, so plasma waves in the longitudinal direction as a function of time. And these plots are obtained by averaging over the transverse width of the speckle. So looking first at perhaps this middle case, so with b equal to 60 oriented in the 2 direction, we get an incredibly clean recurrence pattern here. This is quite a striking result, actually. I think recurrence here is more clean, not because plasma wave damping is stronger, but although we are helped by the fact that the field is oriented in the 2 directions, so trapped particles stay in the speckle, but rather because of the fact that we have this focused Gaussian laser pulse, so its effective intensity is lower, meaning that it interacts with, especially near the boundary, interacts with these previously driven up packets less than it would in 1D. So we get this incredibly uniform, clean recurrence. With the magnetic field oriented in the 3 direction, things are a little bit more smeared out due to the fact that plasma waves are not as effectively damped, but overall things look quite similar. We have very strong and relatively uniform bursts of reflectivity. Now, when we consider b equal to 0, things look quite a bit different. And the initial burst is quite similar, and maybe again this second major burst is of has similar characteristics to what we saw over here. But then the instability sort of enters this period where it's suppressed over the remainder of the simulation. And in fact, when we run the simulation for double the time, this behavior continues. So the instability stays suppressed the longer we run it. This was something we didn't see in 1D, and this is responsible for this slightly larger enhancement that we're seeing over here in 2D than what we saw in 1D. And it turns out that this reduction in the amount of SRS which we're seeing for b equal to 0 corresponds with a nonlinear frequency shift. And this is what I'm plotting in the bottom 2 rows here. So here I'm plotting the Wigner transform of the field. So I'm showing frequency as a function of time at a particular slice in the simulation. And what you see is that the original burst comes in at a frequency of about 0.39. Now, since this plasma wave is, nonlinear, it undergoes this shift to lower frequency here. The next burst similarly undergoes a shift to negative frequency, except the difference is that it came in originally at a lower frequency, so 0.38. And this process sort of repeats or progresses as subsequent bursts come in. They each come in at slightly lower and lower frequency until finally, once we get to this sort of suppressed part of the simulation, we notice that bursts are coming in at significantly lower frequency than where that original strong burst came in. So as those waves are undergoing this nonlinear frequency shift, they also undergo a shift to larger K, and this is in order to maintain resonance with the pump, which of course stays at a fixed omega and K. So the first burst comes in at 1.45, a K of about 1.45. But then we get this sort of slow shift over the course of a couple bursts to a larger K, a K of nearly 1.5. The result of that is that the K lambda debye of these waves increases, so their effective damping increases, and this would be consistent with a suppression of the instability. The instability is entering a more strongly damped regime as a result of this evolution. Now, with the magnetic field, things look quite different, especially in this case in the middle here. So what we see is that the frequency shift of any individual burst is much smaller, and each new burst comes in at essentially the same frequency as the original burst did. And similarly in K, they have each burst has a shift in K corresponding to its shift in omega in order to maintain resonance with the pump. But then each new burst comes in at the original K and omega corresponding to maximum growth. And quite similarly in the case on the right here. So yeah, even though things are a little bit more smeared out, overall, the trend is more similar to the middle case compared to the case on the right, consistent with the differences that we see in plasma wave activity. Now, interestingly, we actually see similar frequency and wave number shifts in 1D as we're seeing here. However, in 1D, we don't get this sort of shut off in the instability like we do here in 2D. Again, this is most likely due to the fact that, or due to the pump geometry, the fact that we have a focused Gaussian pulse rather than a plane wave, which is at peak amplitude everywhere in the box. And so basically what seems to be happening here is that a new mechanism is emerging, or yeah, what's happening, I suppose, is that yeah, the nonlinear frequency shift is emerging as something which detunes the instability in 2D, whereas it didn't have that effect in 1D as a result of the simulation geometry. And furthermore, what we see is that the magnetic field prevents this from happening, leading to a larger enhancement than what we saw in 1D. So to conclude, we've seen that small magnetic fields can mitigate kinetic inflationary SRS at moderate intensity. However, the effect of the magnetic field is more complex as we go to higher intensity. Reflectivity can be similar or even enhanced due to, as we showed, competing effects of the magnetic field. So on the one hand, it can mitigate kinetic inflation as a result of the damping of plasma waves. This suppresses SRS to the extent that inflation is important for growth. But the other effect of it damping plasma waves is that the recurrence pattern is altered, and this can enhance SRS, especially as inflation becomes a little bit less important and these effects are on equal footing. In 2D, reflectivity can be further enhanced due to geometrical effects. Plasma wave damping is less pronounced with the magnetic field. This leads to less suppression than we see in 1D, or less, suppression of kinetic inflation. And furthermore, the nonlinear frequency shift emerges as something which can detune SRS in 2D, and the magnetic field prevents this from occurring. Thanks so much for listening, and I'm happy to take any questions.
Thank you so much.